Let's start. Today we are happy to have Mikhail Kapranov from IPMU, and he will speak about perverse sheaves and resurgence, and he told me that the title is cyclically invariant, so it's the same as resurgent perverse sheaves in the announcement. Mish, please.
Yeah, thank you very much. So I will talk about a report about our work in progress with Jan Soibelman. So about application of perverse sheaves as a framework for resurgence. So the main part of my talk will be sort of uncontroversial statements about perverse sheaves, and then later I will say how they could possibly be applied to resurgence. So in general, so what sort of resurgence is about? It has something to do with, let me put this picture here in the forefront. It is something about, one can say, functions given by divergent series, which we can sort of make sense of using Borel summation and then replace one type of analysis by another type. So from this formal point of view, the kind of hard analytic life happens in the plane, which I have here on the right, which I call the irregular plane. That's the plane where we're dealing with irregular singularities, divergent series, which can be asymptotics of analytic functions. And it's convenient to consider all this behavior happening near infinity of this plane. So in the kind of physical language, this variable z is 1 over the Planck constant. So then we deal near Planck constant being 0 or z being infinite. And there is the other plane, the Borel plane, somehow, which is connected by the original one by the kind of Fourier transform or Laplace transform, in which, seemingly magically, what we get completely different type of analytic functions, which have regular singularities, but possibly many regular singularities, and they are multivalued. And traditionally, discussion of multivalued functions of certain type, of certain restricted type, is captured by the concept of perverse sheaves. That somehow will be the main point of the talk, that we will have some kind of generalizations of perverse sheaves to discuss even more multivalued functions, such as appear in this type of analysis. Well, the procedure of Borel summation is somehow here. Let me put it like this. We start with a series in Z, here on the right, or a series in H, which we can, just for simplicity, let's assume that it starts from the first power of H, or the first power of the inverse. And we do it term-wise Fourier transform, which means we take every term and then the Fourier transform, or the Laplace transforms. So it is a well-known formula that the Fourier transform of a power function is another power function with a gamma function factor. So if we take 1 over z to the n plus 1, we get w to the n over n factorial. So that's remarkable from the point of view of convergence, because the term-wise Fourier transform series has coefficients maybe growing, maybe much slower. And this is called the Borel transform. We just do this term-wise, formally repeat. And this series may converge, and in good examples, it not only converges, it extends to the complex plane, to the W plane, possibly with many singularities, ramifications, and there is some kind of geometric life happening around it, which is completely invisible in the irregular plane. And after this, if we have this function, we can do the inverse Fourier transform or the Laplace transform of that function, so which is written here. And the integral is in quotes, integral from 0 to infinity, because we need to specify the integration contour if we have a multivalued function or a function with singularities. But that is the procedure, and let me just discuss the most classical example, which is in all books and articles on resurgence, it is the Euler series, which is the most retarded series. We have h to the n times n factorial, or h to the n plus 1 times n factorial, rather than divided by n factorial. So of course it diverges. So, but if you do the Laplace, the Borel transform, we just kill the factorials. So we get sum of w to the n, which is the geometric series. And it is an analytic function, but with one singularity. So after that, we can apply the Laplace inverse Laplace transform to this function. So however, there is some kind of residual phenomenon from the fact that the original series was divergent. That the new function has singularity. So we need to specify the contour. A priori, there are two contours here, gamma plus and gamma minus. So we have two candidates for the sum of the series, and they differ by the residue at one, which would give something like e to the 2 pi times e to the minus z. But they both asymptotic to the original series as z goes to infinity. So that's somehow the general pattern. So here on this table, we have the original plane, the z plane, and the W plane. In the W plane, we need to decide how we navigate those singularities. Here, for instance, in this example, we need to decide we go over or under the pole. And this corresponds to what in resurgence theory is known as alien calculus for resurgent functions. Now, if you want to speak about product of the functions in the original plane, this corresponds to convolution at the level of Fourier transform. I'll discuss later the meaning of convolution.
Mish, people might be confused that you threw away zero term of your series started with the first power.
Yes, yes.
Borel transform is just divided each coefficient by n factorial.
Yes.
Which means that your Borel E hat B should start with 1 because it's Wn. It has constant as a first term. Yeah.
What? Well, I may have
go, yeah, stop. Yeah, okay, good. You see, your series E hat starts with, say, h in the first power, and you said that each term is obtained by divided by n factorial, not by n plus 1.
No. Yeah, I think sorry, I'm switching in the first pages. I think this is
you like this. Okay, good.
Yes,
good.
So it's always like this: -1 minus alpha.
Yeah.
So every formula, including say, this is for gamma function. It's also for zeta function is the same. Fourier transform of our function is -1 minus alpha. It's always like this.
Good.
So that's the origin of that trick of starting. Yeah, so basically that, this is the general approach, and this type of analysis is more geometric, and it can be done in terms of perverse sheaves, and possibly some, if needed, some mild generalizations of classical perverse sheaves, which I'll discuss later. So now let me discuss the class sort of, for some time, let me discuss the elementary theory of perverse sheaves. So this subject is kind of so elementary, but there are interesting and kind of deep aspects of it. Suppose we have several finite set of singularities prescribed, set A, we call W1, Wn, and we consider the category of perverse sheaves with singularities in A. So this means that outside of this set A, it is a local system in degree 0, which is extended in appropriate way to those points. The typical example, and in fact, this example covers all perverse sheaves, is the sheaf of solutions or derived solutions of a holonomic regular D model. So we have, just because we have finitely many singularities, we can consider the polynomial Weyl algebra, and if we take a holonomic regular model over this algebra, then it's such things are in one correspondence with perverse sheaves. So now let me describe classical descriptions of such categories of perverse sheaves in the most simple situations. So the basic example is we have one singular point, then a perverse sheaf is described by a diagram formed by two vector spaces known as the vector space of nearby cycles and the vanishing cycles, and the maps A and B in both directions. So the nearby cycles is just a stop of that local system at a generic point. Because of the generic point, it is a local system. The space of vanishing cycles, it kind of measures the jump. So here it's written as cohomology with support in a half plane. So this half plane is suggestive of the Fourier transform, because kind of taking cohomology with support, it means that we take integrals with contours going to infinity in some particular region. So I'll return later to the fact that phi and psi are kind of interchanged by the Fourier transform. And the condition is that 1 minus BA and 1 minus AB are invertible transformations, and they describe the monodromy of the space of nearby cycles, which means of the local system, and a similar monodromy on the vanishing cycles when we rotate this plane. So now, in general, so this is completely trivial and classical. But now let's consider a slightly more general case when we have several points. Then, if we have, near each point, we have the same situation as before. So we have phi and psi. So if we now have a path joining one point with another point, such which avoids all the other points, then we can go from phi to psi in this disk, and now here we get into the stocks of a local system. We're moving to another psi, and then from there we go to another phi. So in this way, we get what can be called the transport map, Mij of gamma from vanishing cycle or at ith point to the vanishing cycles at the j point. So, and of course, it depends on the path. And it is known, one can describe how it depends on the path. So suppose we move the path. It moves the path in such a way that it passes through exactly one point. So then, if we kind of, when we're approaching it closely, then there are two other paths through these points somehow come into existence, alpha and beta. And the abstract Picard-Lefschetz formula, sort of manifestation of Picard-Lefschetz theory without any algebraic varieties, just for perverse sheaves, is that the new transport different from the old transport by the composition of two other transports. This is a quadratic formula, and it appears somehow in many incarnations. To relate it to the classical Picard-Lefschetz theory, we need to consider some particular perverse sheaf, which is associated to a Lefschetz pencil. Lefschetz pencil, in more plain terms, is simply a holomorphic function. Let's say it's a holomorphic function, proper holomorphic map from a complex manifold of dimension n+1 with finitely many, let's say, isolated singularities. In classical Picard-Lefschetz theory, the singularities are quadratic, like here on this example, like Morse, but a priori don't have to be. So there are some number of critical points, and then they correspond to critical values which form the set A. Let's assume that they're all distinct for different critical points. The critical values are distinct. Then we can do the following. We can take the direct image of the constant sheaf. It is a priori a complex. But then the perverse T structure allows us to split each complex, not to split, but kind of slice into its perverse cohomology sheaves, each of which is a perverse sheaf, lies in the perverse category. It's the heart of the T structure. So in the most interesting one, in the appropriate normalization, the zeroth perverse homology, or perverse truncation, let's call it the Lefschetz perverse sheaf. So its phi and psi data are what we get in the classical algebraic geometry. So the phi I is the classical space of vanishing cycles of the function at this point. So if it's a Morse if it's a Morse function, then space is one-dimensional and generated by the classical vanishing cycle, which is somehow here like a little belt around this quadrant. And psi is the middle cohomology of the general file. So, and what I say about Picard-Lefschetz theory for perverse sheaves, if we apply it to this particular perverse sheaves, it will give what's more classically understood by the Picard-Lefschetz theory. So now it's interesting to consider the localized category, in which we quotient by constant sheaves. So we first can say it's a quotient category, which morphism becomes zero if they factor through this subcategory. For such an object, we still have vanishing cycles, and we still have the transports, but the nearby cycles are not defined. It's actually remarkable that we have transports, even though a priori it's defined through the generic, through the psi, and the psi is not invariant, but the transports are defined. An alternative definition is that it is the orthogonal complement of the constant category, which means the perverse sheaves from which home, from the constant sheaf to f, is zero. And what is home? Home is the cohomology. So let's call this category perv zero. So it's kind of the quotient category embeds back. And this, in the classical paper of Sergei Gelfand, McPherson, and Velonen, one can find the description of those categories in terms very similar to classical procedure of singularity theory. So what we need to do, we need to choose a spider, by which we understand a collection of non-intersecting paths joining our points wi with some other point v, which we typically put somewhere at the infinity, and we can call it Vladivostok, which is supposed to be very, very far away. So, and the description is very simple, that the category of perverse sheaves is the category of such diagrams. Basically, it's an amalgamation of the previous descriptions for each wi. We can go from wi to v and have this description. And from the wj to v, have this description. So this is kind of complete amalgamation. But a more interesting part, it is that the localized category is identified with category of diagrams together with some transport maps and monodromies at the point. And the only condition is that monodromies are invertible and the transport maps may be whatever they want. In this description, those transport maps correspond to the path which goes from wi to v and back to wj. That's how it goes. So now, from the point of view of physical applications, it looks a little strange because we carry everything to the Vladivostok and back. So more natural, and this is especially more natural for the Fourier transform point of view, would be the transport corresponding to a straight path, straight interval, assuming that there are no other points on the straight interval. So from wi to wj, we can just go straight. So one can make some minor improvements of these descriptions. So first, of this description of perv bar, first, that it can be considered in terms of transport maps defined for all paths, for straight paths, very complicated paths, any paths which avoid other points, but we want to make them subject to the Picard-Lefschetz relation. This first description, first improvement. Second improvement, that if we associate to object of this category the vanishing cycles, the monodromies, and the rectilinear transports, provided we are in linearly general position, then it's also an equivalence of category. It's an equivalence to this category M, and M was the category here of such diagrams. M was the category of such diagrams. Those are minor improvements you easily deduced. So now let me, from this point of view, we can discuss Fourier transform at the level of perverse sheaves. It is the following. So we start with the perverse sheaf, we convert it to a holonomic regular model, right? And then do the formal Fourier transform. So basically, we say that we want to see the sections of the sheaf as some kind of multivalued functions. So and now what would be the Fourier transforms of those multivalued functions? What we can do, we know what will be the differential equation they will satisfy. We'll just replace in the new variable, which we just take z corresponding to derivative in w, and derivative in z corresponding to minus w. In doing this, the same vector space becomes a model over this ring. But from the point of view of this ring, it is still holonomic, but in general, not regular. So, and we can apply to this holonomic but not regular solution, holonomic but not regular sheaf, the functor of solutions. It will be still perverse. For any holonomic model, regular or not, the complex of solution is still perverse. But it does not by itself describe this model, which is usually expressed by saying that it carries additional Stokes structure. In more convenient, in more standard analytic terms, the Stokes structure means that we're looking at the various rates of exponential growth of the sections of this perverse sheaf, which are some analytic functions. And in this case, at the theoretical level, the answer is known. And let me recall this answer. It is a part of more general statement. I specialize to this case, which is due to Lagrange. And there are several statements here. First of all, so we started with a perverse sheaf with several singularities, but the new perverse sheaf will have only one singularity. Moreover, only one singularity at zero. Moreover, at this 0 point, the singularity of the new D model is regular. So since we have a perverse sheaf only with one singularity, it's topologically as a perverse sheaf is described by phi and psi. So here is a misprint, should be also phi of f check. And one can say what they would be. So the psi of f check, the generic fiber, will be isomorphic to the direct sum of all the vanishing cycles. And actually that's interesting for several reasons. So it depends only on the class of f in the localized category. And the vanishing cycles of the new sheaf at the point 0 is just the generic stock of the old one. So if we are interested only in the neighborhood of the infinity, where the irregularity actually happens, because at 0 is just a regular singularity, then we only care about objects of this category. So there were several earlier papers describing the Stokes behavior of this sheaf near infinity. And in our paper with Jan and Leo Sohanov, we gave a formula which describes the Stokes matrix. So one can sort of study this systematically. There are local Stokes matrices, global Stokes matrices. I'll describe. So in this case, some kind of the one matrix which characterizes this thing, it expressed in terms of rectilinear Mij, in terms of convex geometry, in a form very similar to what is used in the so-called algebra of the infrared of Gayota-Moore with certain convex paths and so on. But this done in case when A is in linearly general position. So now let me discuss the concept of convolution. The general principle is that multiplication of functions in the z variable corresponds to convolution of functions in the w variable. So, however, at the analytic level, there is a little ambiguity as to what do we call convolutions. So, for one way of doing this would be to have this formula: integral not over the entire line or plane, not on the infinite contour, but on a finite contour. Integral from 0 to w, f of u, g of w minus u.
Mish, what means two curly brackets?
Oh, it means convergent series. Series converging somewhere in the neighborhood.
I thought that one used just one pair of brackets, but
okay, yeah, I don't know.
Yeah, okay, but these are just germs. I mean, that...
yes, just germs. Yes, just germs. Yeah. The first thing that if you have two such functions, then you get this. So one can write actually formula.
I'm not sure about your integration from 0 to w.
But that's what you can do for analytic functions. In usual real analysis, you probably would go for a sort of
all to the infinite.
To infinity, yes. But it's sort of, as I said, there are different versions here, which sort of
thank you.
It takes sometimes an effort to reconcile them. So let's do exactly this. So then we can say
you can think that, I mean, this is an integral of a straight interval.
Over straight, yeah. Not only the point is not only in the straight interval; it is the integral in not natural limits.
In the very small,
neighborhood
of the zero.
Yes, and this has some consequences. So, but this first of all is that the easy consequence that we can write the formula for the coefficients, and it will be such that it will start with, it will have no constant term. For instance, if you convolute the function which is identically 1 with itself, we get a function w. However, so the advantage of this is that is a version of, so let me just say that many people know the Holonomic's theorem on multiplication of singularities. If you have two power series, some a n z to the n, say a n say w to the n, and b n w to the n, we'll write the product a n b n w to the n. That's the most retarded thing one can do. And the Holonomic's theorem says that the singularities of the new function are products of the singularities of original function. And the proof of that is that if you multiply the coefficients, nth coefficient by nth coefficient, that's convolute, that's product in terms of Fourier transform on the abelian group Z, product in functions on Z corresponds to convolution on the dual, on the Petrarchan dual group, which is the circle. So there is an integral formula for that, this convolution. And in the complex domain, you can deform the contour. So now what I'm talking about here is an additive version of this. And I'm saying this, and suppose f, which was not just a germ, but extends to some multivalued analytic function with singularities in a possibly infinite set A. And G has the same thing for B. Then the convolution has singularities in the set A united with B united with A plus B. So that appearance of A and B here, rather than just A plus B, as would be the case for the original Holonomic's theorem, is due to the fact that this this contour of integration is not in natural limits, as it would be if it did it over the circle. But nevertheless, one can prove this by deforming the contour. And I say here it's very robust. It means that it basically, no matter how, no matter how bold general assumptions we make, it is possible to adjust the proof by deforming the contour. So first we can say that suppose two functions are, say, meromorphic. They have singularities, they have poles, right, and some points, and that's a single value. Then it's relatively easy to prove this. But even if they are multivalued, then you deform the contour, so to say, in the Riemann surface, and the same statement holds. That's kind of a remarkable statement. Now, there is a companion theory for perverse sheaves, which is due to Nick Katz for a long time ago, both additive and multiplicative case. So in several books in Princeton Red series, which people know, we have two perverse sheaves. We do basically the same thing. We have the addition map from C cross C to C. We have their external product, and we can take the direct image. So basically integrate over the fibers. So, but here we integrate over the entire fiber rather than over the interval. So, but there are two ways of doing this. We can do direct image, Schrick direct image, and star direct image. And a priori, we get two candidates for the convolution, united with a canonical map. So the elementary theory of this, at least it's elementary if we apply it to this case of over complex numbers. But first of all, the difference between those two lie in the category of constant sheaves. So both of them gave the same operation on the localized category. And if you lift them to actual perverse sheaves, as I described before, then this is represented by the middle convolution. So if those are perverse sheaves with no cohomology, then both of those are perverse. And so you take the image in the perverse category, and the image will be again in perv zero category.
Mish, you used interchangeably perv zero and perv with a bar, or what?
No, I'm saying two things. That first of all, the difference between those things disappears in perv bar, and second, this canonical thing in perv bar can be realized as the image.
I thought that perv bar and perv zero are equivalent.
No, equivalent, but perv zero is embedded.
Ah, you mean, okay, yeah.
Is embedded, and we can give an independent kind of slightly different definition. So when people say middle convolution, it kind of has this aura of mystique. What is middle about it? So it simply means that you take an image of this map. This image of this map, it will again lie in the full perverse category, and it will lie in perv zero.
Mm-hmm.
I'm just summarizing the theory of Katz in this simple situation. And the vanishing cycles of the convolution is basically tensor product. Tensor product over this. That's one thing. And at the level of Fourier transforms, the Fourier transform of the convolution will be the tensor product of the Fourier transforms, at least as local systems or even irregular connections outside zero. So the convolution takes, Fourier transform takes convolution to the tensor product. So now one feature which always attracts the eyes when reading about resurgence is what people call the alien calculus. And let me describe how it can be lifted to manipulations with perverse sheaves in the same way as Fourier transform for perverse sheaves somehow lifts the Fourier transforms for actual analytic functions. So suppose we have a perverse sheaf, and we have set A of singularities. I still assume it's finite, but maybe not in linearly general position. which means the sum of the points may be aligned. So now I said before that's very natural to go from point A to point B by straight interval. But if there are other points on this straight interval, then it is not clear how to go. Well, we can specify by a sort of sequence of signs. We can say minus sign. So we go either left or right. And we have 2 to the r possibilities when r is the number of intermediate points. So if we have a sequence of signs, epsilon, then we have MAB epsilon from phi A to phi B. In particular, we can have the most naive one, when we go everywhere on the right. So this is the plus transport. So if there is nothing in between, that they're all the same. Now it turns out that this plus transform satisfies certain satisfies certain group-like property, and it is very natural to take a version of the logarithmic series of this. So what is written here is that we go. Maybe I'll scroll back a little again. So we go to an intermediate point, again, with all pluses, and then to another intermediate point with all pluses, and so on, and take all such possible compositions and write this logarithmic series. So it's a map from phi A to phi B. And it terminates because there is only finitely many possibilities how we can subdivide this into steps. But if you apply the Picard-Lefschetz formula to this, so what is here? This is one m sort of ends and another m begins. So this sort of corresponds to the difference by the Picard-Lefschetz formula corresponds to the difference between going up and going down. So if we write it more explicitly, it will be interesting. We recover the formulas in the analytic theory of Ecalle. So first of all, this transport is a linear combination of the different epsilon transports with positive coefficients. The positive coefficients sum to 1. And the coefficients I is just number of pluses, factorial of the number of pluses, times factorial number of minuses, divided by r plus 1 factorial. It's interesting that we apply the alternating series to this thing, and we get sum of positive terms. So simple examples would be like this. So for one and so if there is nothing, it is the straightforward transport. If there is one point, that is sort of half upper transform, half lower transform. If there are 2 points, then again there's simple coefficients, 1/3, 1/6, and so on. And what's interesting about this, that it is, as I say here, stable under introducing dummy singularities, which means that if I put here some point A2 and pretend that there is singularity while there isn't, then this thing will specialize to this. Basically because 1/6 plus 1/3 is 1/2. So, and the proper Alien derivative would be an endomorphism of the total space of vanishing cycles. So it's written here. So it's given by, if you have any element W and C, then we can do the matrix elements such only if, which is non-zero if only if the points differ by W, and in which case is the alien derivative transport. So of course for most W or omega, maybe I should say this is omega W, this for a given sheaf, this is 0. So recall that for the convolution, the total space of vanishing cycles is the Tensor product. And what's interesting, sort of it's a conceptual version of the statements in resurgence theory that alien derivatives are derivatives. So with respect to convolution, with respect to this identification, the alien derivatives satisfy the Leibniz rule. From here, one can construct the Stokes matrices for the Fourier transform. And here I will talk about local Stokes matrices. Let me sort of explain what it is about. So we start with some direction in the z-plane. If it's a direction is generic for us, if those half lines a plus r plus zeta issuing from all points of A are disjoint. So in this case, the stock of the dual of the Fourier transform sheaf is the cohomology of the original sheaf with support in certain half plane of slope zeta, which is shifted so that it contains all those half lines. And if so, then by excision or homotopy, it can be identified with cohomology with support in the union of those lines, because sort of outside of them, everything is locally constant. And cohomology with support on the union of lines is a direct sum of cohomology with support on lines, and those are the vanishing circles. So we have an identification of the stock at zeta with the direct sum of vanishing circles. But now, if zeta is a slope of some interval, then it's called the Stokes direction. And in this case, there is some ambiguity. So first of all, that identification breaks down because they will intersect. But if you go a little bit on the left and a little bit on the right of this direction, then we have two identifications which we connect with monodromy. So we have a transformation or a matrix, if you wish, from direct sum of vanishing cycles to itself, which can be called the local Stokes matrix in direction z.
Mish, in this Malgrange theory or whatever, irregular singularities, so there is a canonically defined object which is kind of a local system with filtration, with jumps. And you kind of
yes. One can also somehow do this, and basically jumps correspond to how far. So the filtration corresponds to what's called the. So if to the real part of W zeta to the it's somehow the growth of the corresponding exponential contributions. So it's more or less built in the same picture. So the filtration changes when they become parallel.
And actually for symplectic topologies, because there are symplectic topologies in the room, in the virtual room, it's the same story as with Lefschetz symbols. So
yes. Those are exactly, yes. If we apply it to that particular perverse sheaf, which I talked about before, we'll get the Lefschetz symbols, yes. So the phi will be, each phi A will be one-dimensional, and those will represent Lefschetz symbols. And those are sort of Lefschetz symbols with coefficients in arbitrary perverse sheaf. Yeah. So basically, what we have a change of basis from this bunch of symbols to this bunch of symbols, and from z plus to zeta minus. And then one can find relatively easily, it's a version of, again, Picard-Lefschetz theorem, that the matrix element of this seed zeta is actually given to M plus transport. So it's a unipotent matrix. As usual, the Stokes matrix is unipotent matrix, it's upper triangular. In fact, it will be upper triangular in the following sense. So the matrix elements from A to B will be 0 unless the slope of the interval AB is equal to zeta. They go, matrix element go only in this direction, only in the direction zeta. And as a corollary, so the logarithm of this is a sum of the Allen derivative. So that can be called Allen derivative in the direction zeta. So maybe I should say that the seed zeta would be multiplicative under convolution, and the logarithm of it will be additive under convolution. So this is somehow a kind of embellishments of elementary theory of perverse sheaves, which are have the flavor of resurgence. Of the
Miss, again, for, I don't know, symplectic topologist or differential equation people. So multiplicative means that it's a Stokes automorphism or isomorphism.
No, it means that for tensor products, it is a tensor for the
okay. With respect
multiplicative.
To tensor,
yes. Okay. So far, I'll scroll back a little.
Yeah, multiplicative with respect to convolution. Yeah, that's
to convolution, and so to this situation. So this type of thing. So, sorry.
Yeah, that's fine.
So this is multiplicative. So we're basically thinking in terms of the tensor category, and this delta omega is some kind of derivation, but of the identity factor of this tensor category.
Yeah, and in order to see this formula, you should remember that for the convolution, you have tensor product of two vector spaces.
Yes.
Yeah,
yes. To remember this. Yeah. Okay. So now. Okay. Let's check.
Actually, Mikhail, in that tensor products, so
what?
The tensor products of the two perverse sheaves, are you talking about in terms of diagrams or?
No, I mean tensor product as local system outside zero. So let's not worry about behavior at zero.
Okay.
Let's consider as irregular data, irregular connection outside zero, irregular at infinity.
Okay.
Yeah.
Okay.
So from this, somehow our suggestion or plan is that we should consider the perverse sheaves or objects of the localized category, which are algebras with respect to convolution. Maybe commutative, maybe not. So something like f star f going to f. So now, here, if we go down this path, it calls for some new features. So first of all, for non-trivial examples, the set A should be a semigroup, because the convolution for the singularities for f star f is set of sums, A plus A. So A should be should be infinite.
Semigroup or monoid?
Or monoid, maybe, yeah, monoid. No, sorry. Well, in the examples, it will be a semigroup. Sorry, it would be a monoid, yeah. So a good setup would be that the vanishing cycles at those infinitely many points should be finite dimensional spaces. But if you want to think in terms of nearby cycles, it will be infinite dimensional. So nearby cycles, so sections of this local system outside A are intuitively those multivalued functions we are dealing with. But all the formalism is hidden in the vanishing cycles. So a definition in terms of MAB, in terms of transports, would still make sense. Fourier, what's called the transport subject to Picard-Lefschetz identities. So, and if you do this, then we can define delta W. There will be derivations of an algebra, because there were derivations in the sense of tensor category. If you have an algebra in this category, then on this it will be an algebra derivation. And the dual thing would be a local system of algebras, algebra with respect to tensor product. and Stokes matrices will be algebra automorphisms. So this is the framework which kind of interesting to consider. Algebra automorphisms, which are coordinate changes. If you think of automorphism of commutative algebra, it's a change of coordinates in algebra geometric sense. What's another thing? So what I want to say here, that in fact, the set A may even be not discrete, such as, for example, the image of a free abelian group, so symplectic lattice, under some map into the complex plane. So now this may seems counterintuitive, but it is possible to consider multivalued functions with a dense set of singularities or with a dense set of periods if they are multivalued. For example, the most famous analytic function is the inverse of an abelian integral. So as we know, the inverse of an elliptic integral is an elliptic function. It has a period, it has two periods. But if we consider inverse of abelian integral in higher genus, so it would be it will have, say, if genus 2, it will have 4 periods. And this prevented people in the 19th century from considering such inverses. Only by the Abel-Jacobi formalism, they consider several integrals at once, and then they had a discrete. But a priori, if we have this function, we can have its composition inverse. And for an abelian integral, it will be periodic with respect to a dense abelian group. Now, how could it be possible? Because it's multivalued. We go from one point to a singularity, go around it, we go to a new sheet of Riemann surface, there is another singularity, go around it, and so on. And altogether, it may happen, and it happens often, that the set of those singularities on the Riemann surface, when projected to our complex plane, will be dense. And there is nothing wrong with this. There is this type of highly ramified Riemann surface over the complex plane. Now, if we understand the legitimacy of such coverings, then we see that there is a corresponding concept of constructible sheaves. So you see, every sheaf is described by in terms of its Ecalle space. So locally, there is some kind of covering, but one can have those coverings, the sort of continuation of such sections of such sheaves having exactly this type of behavior. So in principle, it is not impossible. So I want to consider discuss two possible types of examples. One is example underlying theory of Donaldson Thomas invariant of Kontsevich Soibelman and Gayotomov-Neitske, where cluster transformations were interpreted as some kind of Stokes matrices. Let me recall this situation. So we have a torus, a symplectic algebraic torus, which can spectrum of the group algebra of a lattice z to the n. It has a monomial basis of x alpha to the gamma. There is a central charge map into C. So our set A will be the image of this. So let's consider for now the case when n equals 1 and gamma is z2. So it can be discrete. So in this case, sort of the most celebrated formula in this theory is the birational cluster transformation, which on the level of monomials is this, that x alpha is sent into x alpha corresponding to each gamma. Each gamma gives a birational transformation, which multiplies x alpha by some power of 1 minus x gamma, with omega of gamma is the Donaldson-Thomas invariant. So let's look at this matrix. Let's look at this as a matrix in the basis of monomials. So we see that the matrix elements are non-zero only in the direction gamma. So x alpha will be sent to x alpha plus something times x alpha plus gamma plus something times x alpha plus 2 gamma plus so on. Only in this direction. So it behaves exactly like the Stokes matrix for the Fourier transform of some perverse sheaf. Some perverse sheaf with this set of singularities.
The
So
sum can be infinite, yeah.
Yes, this perverse sheaf with this set alpha, which is whose singularity, set of singularity is A, which is the image is Z of gamma. So this kind of, there is some perverse sheaf which suggests itself. So it will have one-dimensional spaces of vanishing cycles everywhere, and the transports would be read off. Transport from A to B would be read off from the matrix elements of K gamma, where gamma is on the slope from alpha to beta. So we just redo all the formulas before, sort of, they kind of want to apply themselves here. Or even better, so I forgot to say here that an easier formula would be obtained if we do the alien derivative transport. It would be easier because there will be some sum here. Sort of all the known formulas in this theory, they kind of want to combine into a description of perverse sheaf. So, and this relatively, it's interesting to study it in more detail. We understand some parts of it, but not yet fully. And
actually, maybe since you know it's interactive talk, so that's some comment here. Before kind of our work with Maxim, Joyce tried to construct some invariants of Calabi-Yau threefolds, which in the end it's Donaldson-Thomas invariants. And since he used generating functions of those invariants, his formulas were additive.
Yes.
And just probably when we go,
and they would exactly match the alien derivatives. Yes, I thought I have written it here, but I haven't. I forgot. Yes, in my mind there was a place here when I have written it, but unfortunately.
But there is one, I don't know, caveat or maybe just remark. You see this omega, which is an important additional structure. Sometimes people define K gamma without omega and write the product as K gamma in the power omega.
Yes, it's the same exactly.
Yeah. But the thing is, I mean, and it's kind of when you look at those Joyce formulas and compare with others, especially when you try to compute something on the computer, you'll see that Joyce formulas contain many summands which are equal to zero, some unnecessary summands. And this is because this omega of gamma kind of they are not all equal to 1, for example. Some of them are equal to 0. So which means that when we use this alien derivative, if you'd like, version, there might be kind of too many summands which we can get rid of and which are not do not appear when we use a multiplicative version.
Yes. You're right. Yes. So that's one example, and another example is the cohomological whole algebras. Let me again consider some finite dimensional version. What does it typically say? That we have a quiver, we have a cyclic word in this quiver, then we have a potential out of this cyclic word on each representation space. Is a trace of this cyclic word. So representation space is a stack. And we have, so the WD is a function of this stack. So in this additive in short exact sequences, this because it's a trace. The usual coha is simply direct sum of cohomology of those stacks with coefficients in the vanishing cycles with respect to this potential of the constant sheaf. Now this sort of again suggests itself that there should lead to a convolution algebra, non-commutative, in which we have instead of doing the full cohomology, we sort of do the intermediate step. We take the Lefschetz perverse sheaf of this. And that would be an algebra with respect to convolution, which would somehow the new thing would be that it will have not just those spaces, but it will have also transports between them. Somehow this will be the refining of the coha structure. So not just the spaces, but also transport between vanishing cycles at different values. And probably similarly, we should have a similar situation for the Chern-Simons functional, which will be an infinite dimensional example. So there, of course, there's a usual subtlety with orientation data, because the cohomology should be the semi-infinite cohomology, and like in any semi-infinite situation, we have this. So that's another possible example of convolution algebra, which kind of naturally suggests itself. So I'll probably stop here. Thank you so much.
Thank you very much. Mish, in this last story, you see that this coha is probably, I don't know, graded vector space or whatever. Not an algebra.
Yeah, this is graded. Yes. So
no, but no. I mean different thing. I mean this omega DT invariants which appeared on the previous page, but which are missing here. Because when you consider convolution, you see when you consider these perverse sheaves and different critical values of the potential, you do not have kind of omegas which are indeed DT invariants for the three Calabi-Yau category associated with the quiver with the potential. You get the same number of gradient lines, some kind of a standard story, which with the Lefschetz perverse sheaf. But there is also stratification of that stack, AFD, by Gardner-Riemann types.
Yes.
And this structure seems to be kind of it does not agree with this convolution.
Yes. You are saying that the previous situation with omega, it had to do something with the stability, and then how the whole thing varies when we change the stability. And here we ignore stability. Yes.
At least we ignore stability on the category.
Yes, and here it's not clear. I don't know what to say. Clearly, there should be some sort of unified statement here, because you're absolutely right that Donaldson-Thomas invariant are present in this context as well, but they're not seen here.
Yeah, it's kind of a framework which might be. Maybe its categorification might be useful for people doing Landau-Ginzburg models, but this DT invariant story with the cluster, with the clusters on your previous page, it's somehow a bit puzzling me, because from one side, when you do DT theory on Calabi-Yau threefolds, it's not technically, it's not a Landau-Ginzburg model.
That's right.
On one hand, but on the other hand, there are some. There is something. For example, again, there is a potential on the stack of coherent sheaves on the Calabi-Yau threefold coming from Calabi-Yau structure, and then you can construct this coha stuff. You have this.
You mean the holomorphic Chern-Simons function?
Yeah, holomorphic Chern-Simons, and actually Pierrick Bousseau claims that DT invariants for this Calabi-Yau threefold are the same as those coming from that but it's not really holomorphic Chern-Simons. He says that there are two complex Lagrangian submanifolds in the complex manifold. One is kind of the complex manifold we are talking about. It's something like Hitchin system. It's complex integrable system. One Lagrangian is a fiber, but the other one is quite complicated. It's kind of, it's not, in the case when it's really Hitchin system, it's called Hitchin section, but in general, there is no explicit construction. It's only on the level of physics. Then you consider paths to infinity with endpoints, and you consider the functional on the space of paths, and then you do Landau-Ginzburg on this infinite domain. And he claimed that you obtain the same answer, which is kind of, so on one hand side, this story with omegas and this cluster, it's different from Landau-Ginzburg model, but there are some people who claim that it's the same.
So yes, you basically say that perverse sheaf, which sort of constructed formally, could possibly be obtained as the Lefschetz perverse sheaf or some. Yes.
Some kind of very complicated.
That's possible. Yes, of course. Yes.
Okay. Yeah. All right. So more questions? Yeah, it's all very new, so people probably need time to digest. Yeah.
Definitely.
Okay.
So all the perverse shifts are actually living on the complex plane, right?
Yes, in one dimension, yeah.
It's just one-dimensional.
Only, yes.
And so here the singularity actually is just you're dealing on the D-module side of...
Yes, except it's non-classical in the sense that they have infinitely many singularities. And if we have infinitely many singularities with vanishing cycles, say even one-dimensional, then the generic fiber may be infinite dimensional. And this kind of more harder to define.
I see.
So for example, let me give another example. Suppose we have phi A equals C and monodromy is always -1. Then it means that we have a function with quadratic ramification at every point. So probably a Riemann surface which ramifies quadratically have one quadratic ramification around each point. So it means that the sort of total number of sheets will be infinite.
Okay, I see.
Yeah, something like that.
So you give a categorical description of this sort of perverse sheaf or the
categorical description
modules with the singularity.
No, in the model with the modulus is not clear because it's infinite dimension. But in terms of transport, we can describe it.
I see. So when you have when you earlier you described that you have a given X, and you assume that's some kind of a smooth complex manifold, and you have a function W, the potential, and then you construct this category. And here, when you were so are you taking this perverse sheaf on complex numbers, taking values inside of that category, or?
No. It is just a direct, in the previous situation, it was just a direct image. We take the direct image of the constant sheaf and then do the kind of extract the interesting perverse part.
I see. So with the specified singularities.
Yes, with specified singularities, yeah. It's like saying when you do exponential integral, you first integrate, you have e to the lambda f, yes, f of x. Then you first integrate over the fibers, and they take one-dimensional Fourier transform.
Okay. On a separate question, probably, I've heard anything about the Stokes phenomena, which also dealing by the divergence.
Yes, it's exactly built into this situation. Yeah, of course.
The divergence series says what kind of sectors when you move, but you can have an expression, but once you reach to a point that you have to go through some kind of jumps.
Yes, but this is exactly what described, what I described before.
So this is what you meant Stokes
jump,
structure, right?
Yes. This jump. I don't know why it is colored. Yeah.
Unless you clicked on it.
It's highlighted.
I clicked something. Okay. So yeah, so this jumps is precisely the Stokes matrix. The change in
Okay, I see. Okay.
So that some of the leading asymptotics change. Yeah.
Mish, but for those who remember the beginning of your talk, you mentioned that Resurgence is a machine which converts divergent series into convergent. And your kind of, the rest of your discussion was sort of pure algebraic, but maybe infinite. So this
yes.
divergence is.
I'm saying that it converges. It converges irregular behavior into multivalued behavior with many singularities that are described by Perverse sheaf.
Okay, so it's rather a machine which converts irregular to regular, and
yes.
But the fact that these divergent series somehow appear in the irregular story, it's sort of.
No, it is typically as asymptotics.
I mean, it's because typically, kind of commenting on Zhongzhu's question, typically you have like finitely many, say, in classical story, finitely many Stokes rays, which divide your plane into finitely many Stokes sectors. And so you consider formal solutions. So at each sector is the same series which diverges. And you kind of make them convergent using Stokes.
Then it would be exactly this type of behavior, yes.
And another question is, everything indeed is one-dimensional. Yeah, you consider D modules of perverse sheaves.
Yes.
All right, but there are perverse sheaves on vector spaces. There is Fourier transform. What?
Yes, but so somehow nobody considered. Nobody has like a remote idea what should be resurgence in higher dimensions.
But in your story, you don't have
maybe irrelevant. So let me scroll a little. Irrelevant. Let me scroll to the discussion of convolution. Let me scroll to this. To the discussion of convolution. Scroll to the previous one. I'll
you mean the sneak cut story?
No. To discussion of holonomic theory.
Oh, okay.
Oh, I'm sorry, I just cannot navigate this. Just a moment. Please don't look at this. It acquires a life of its own. I don't know what it's doing. I cannot stop it. Stop.
No. It counts how many times you hit the. But people have your.
Yes, but okay. I just. I'll get there just now. Yes. So in one dimension, the Hadamard theorem is that the singularities of the convolution are the sums of singularities. Right? Roughly.
Mm-hmm.
Now, in two variables, this cannot be true. Because singularities form a divisor. Right? So the sum of them will fill the entire space. So what is the corresponding answer? The answer is that we need to look at the map of the product map of the product of the divisors and take the discriminant of this map, where the preimage looks different from the generic thing. So it's much more complicated behavior.
Yeah, so this algebra structure is not...
No, the algebra may be okay, but this set of the operation on
multivalued analytic functions are much more complicated.
Yes.
Yeah. And so in that case, the convolution product will be just a multi-integral.
Yes,
this is not a problem.
We can define it, but and one can say what is the singularity, but you won't like the answer. The answer is such you a priori you won't like it.
And the same is true for convolution of perverse sheaves. Yeah.
And the same is true for convolution of perverse sheaves.
Yeah. So in this case, actually,
there is an answer, but you won't like it. Yeah.
I was going to ask how you integrate if 1 over x, 1 over w, if that appears from 0 to w.
I don't know. So this definition is like this. We start with convergence. We start with convergent things. That is how it goes. Yeah. 1 over w cannot do it, of course.
Yeah, so because of the log, I mean, basically I was talking in the integral should be log of w.
Yes.
Minus log of 0.
Yes.
Okay, more questions? Last chance. Well, if there are no more questions, so thank you, Misha, very much for very interesting and inspiring talk. And yeah, so then this is it for today's seminar.